All right, so we've got an interesting equation here, and we want to show that this expression is equal to Euler's constant. So what we want to do is to first consider this particular one. So if I should say 1 plus 1 over n to the power of n. So I want to make use of my binomial. All right, so using my binomial, this will be equal to 1 plus n into 1 over n using the knowledge of binomial expansion. What do I mean by binomial expansion? I mean, if I should have 1 plus x raised to the power of n, remember this is equals to 1 plus nx plus n into n minus 1 over 2 factorial x squared n minus 1 n minus 2 3 factorial x cubed, like that. So this is what I want to use to express this. So this is my x in this case, and this is my n, right? So yes, 1 then plus nx plus my n is still my n into n minus 1 over 2 factorial. Then my x here is 1 over n power of 2, then plus n into n minus 1 n minus 2, then over 3 factorial 1 over n x cubed, then on and on. All right, so if this cancels this, I would have 1 plus 1, because this cancels this here, this 1. Then this is going to be 1 over n squared. So this n squared here cancels this n, so I still have plus n minus 1 over 2 factorial is just 2. So let me just say 2n plus, then this one here is going to give me n into n squared. If I should do this minus 2, that's plus 3n minus 3n plus 2, then over 6n squared over 6n cubed, right? Instead, then plus so on and on. So if I'm to continue with this, that would be that, yes, I have all of this. If I should take this out of this, there's still 1 remaining. So I have 1 plus 1 plus n minus 1 over 2n plus, so the whole of this out, n squared minus 3n plus 2 over 6n squared, right? Then on and on. So this expression represents just this one. So I'll take the limit to infinity of the n. So if I should take the limits to infinity, n to infinity. So this only concerns where I have n. So I don't have any business with this ones. So it still be 1 plus 1 plus. So to make this make sense, since I have the same degree, I'll divide by the highest degree. So this will be 1 minus 1 over n over 2 divided by n. Then what else I'm going to do is divide this by n squared. So that would be 1 minus 3 over n plus 2 over n squared, then over 6, right? Plus on and on. So if I should fix this infinity into all of these expressions, then let's see what we have here. Then I would have instead infinity here. 1 over infinity is going to be 0. So here is remaining 1 plus 1, then plus 1 over 2 here. Then this is going to be 0. This is going to be 0. Then this could be 1 over 6, and it goes on and on. So how does this gives us Euler, right? So let's see quickly how this corresponds to what we did. So for Maclaurin series, so let me write from Maclaurin. For Maclaurin, we are made to understand that e raised to the power of x is equals to 1 plus x squared over 2 factorial plus x cubed over 3 factorial, then on and on. So for x to be equals to 1, when x is equals to 1 here, that will be e raised to power 1. That is still e. That's 1 plus 1. Then plus 1 square is 1. 2 factorial is 2. Then this is 1 over 6. You can see that this here is still what we have here. So I can say this is e. Alright, and that proves it. Now, how does this correspond to this? And that's the answer it here. So if I should take the summation, for summation, this, when n start from 0, 1 to n factorial. So when n is 0, that's 1 over 0 factorial. That's 1 over 0 factorial. When n is 1, 1 over 1 factorial. When n is 2, 1 over 2 factorial. 1 over 3 factorial, like that. So 0 factorial is still 1. So that's going to be 1 plus 1 plus 1 over 2 plus 1 over 6. And we still have our e. So therefore, e is equal to the limit as n tends to infinity, 1 plus 1 over n is the power of n. Or you can say is the summation of 1 over n factorial, but it has to start from 0 and goes to infinity. That's how to solve it. So don't forget to like, share, and subscribe to this channel so you can see more videos of this nature. I'll see you in the next video.